Welcome back. Today we're going to be finishing chapter 2. We're going to talk about histograms, and then we're also going to talk about some other types of graphs as well. We're going to look at how to use your graphing calculator and StatCrunch to do histograms. So if you don't have your calculator out, I would go ahead and get that out because we will be using it quite a bit today. Okay, so we've talked in the previous section about frequency distributions and how they're helpful for summarizing data. A histogram is an even better tool because it visually lets us interpret some of the data that we're trying to summarize and investigate, and we can see some of the key characteristics of it a little bit more clearly in the form of a histogram. So a histogram is a graph that consists of bars of equal width with drawn adjacent to each other. So there should not be any gaps between the bars unless there are actual gaps in the data. So if you have a class that has 0 as the frequency, then you may have gaps, but otherwise the bars should be touching each other, and that's what we mean by drawn adjacent to each other. Another characteristic of a histogram is that the horizontal scale, or your x-axis, is going to represent quantitative data values, and this is in contrast to a bar graph. A bar graph, the x-axis or horizontal scale, can represent categorical or qualitative data values or quantitative. So the histogram is going to be the quantitative data values. Your vertical scale is typically going to be represented by the frequency or a relative frequency, one or the other. Okay, so the heights of the bars are going to correspond to your frequency values in most cases. Okay, so this is just a visual to show the difference. Here's your histogram. You've got your bars that touch each other. We do have a gap, but it's simply because there were no data values for these two classes. And you do have numeric values across the bottom. This one's a little bit hard to read, but you can see our bars are not touching each other. And we also have, this is A, B, C, D, and E across the bottom. So it's not numeric data, it's categorical data that's being represented here. Okay, some important uses of the histogram, and probably one of the most important, is to visually display the shape of the distribution. So we'll talk about shapes of distributions a little bit later today, but we want to know, is it normally distributed? Is it uniformly distributed? And the histogram is going to show us those kind of things. It'll also show us kind of the center of the data. It'll show how spread out the data is, and it'll also help us to identify any outliers of the data. Okay, this is the example that we worked on last class, the McDonald's lunch service times. So if you don't still have this in your calculator, take a minute to enter this in L1 in your calculator. We went through that process last class. So get everything entered in L1, and then we're going to look at how to do a histogram on your calculator. Okay, just to kind of recap, this is how we did the frequency table that went with that data set. We started it at 75 and we had a class width of 50. That's going to be important as we build our histogram using our calculator. So, so at this point, I'm going to leave this screen and go to my calculator. So picking back up with the calculator here, you should have your data all entered in L1. I have another example in L2, so just disregard this for the time being, just as long as you have your data entered in L1. So in order to construct our histogram using the calculator, we're going to go to second and y equals and bring up the stat plot menu. And I don't think it took second and stat plot. Okay, so here we are, and we're going to choose the first one. We want to make sure that these others are turned off. If they're not turned off, then go in and do that, because that will be important as we go forward, and you'll get error messages if you've got more than one on in a lot of cases. Okay, so once we bring up plot 1, we'll make sure it's on. You want to use the arrow keys. So we'll just use these arrow keys to go down and over, and then click enter because we want to highlight this third graph, which is the histogram graph. And then for the X list, you want to put whichever list your data is in. So my data was in L1, so I want to make sure L1 is here. If I switch to that other set of data that I had, then I'm going to need to go back and change this to L2. Okay, once we have, I'm not going to mess with any of this other. If you want to change the color, then that's kind of personal preference. So we're going to go and we're going to press zoom, and we're going to choose number 9. Zoom 9 is zoom stat. What that does, we're going to use that a lot in this class because it takes the data set and it looks at it, and it helps us to pick a good window for the data. So we're going to choose zoom 9, and you'll see a graph that comes up like this. I want to compare this to the graph that we generated ourselves last time. Okay, so this is the graph that we had last time, and we had 5 classes here, and you can see our classes started at 75 and went to 325. When we go back and look at what the calculator gave us, we have 1, 2, 3, 4, 5, 6, 7, 8 classes that are showing here. So the general shape of the graphs are the same, but what we see is that the number of classes is different. So if we want this graph to actually match up with the one that we did by hand last time, what we're going to do is we're going to go over to our calculator, press window, and we're going to make a few changes. The first change we're going to do is X min. We're going to change that to 75. That was our starting place. The other part, I'm not as concerned about the X max. If you want to change that to the 325, you can do that. And the X scale, we want the X scale to represent our class width. So our class width, if you recall, was 50. So once we've made those changes and we press graph, what you see is we now have the 5 classes that we need, but we're cutting the top off of this graph here. So we're going to go back in and make one more change, and that change is going to be our Y max. Y max is representing the height of the graph, basically. We know that 24 was the largest frequency for this particular graph, and so I'm going to go up to 25 just to have a little clearance there on it, and press graph. And what you see is a graph that's very similar to the one that we had generated by hand there. Okay, so if you compare them, they look very much alike. If we go here on this one, okay, if we go to this one and we want to look at how many is in, what the frequency of each one of these bars is, if we press trace, okay, and then use the arrow keys to toggle over, we can see that N is going to represent the frequency for each one of these. So if we move over, then you can see that changes for each class, and it should correspond with the frequency table that we had created for that particular example with 5 classes. Okay, so here is the data that we use for the Old Faithful geyser. So I'd like for you to try generating the histogram on your calculator using this data, and then we'll take a look at what you should have gotten. Second and stat plot, and we want to go to number 1, make sure that it's turned on, and make sure that the third graph is highlighted, and then we're going to go down and we want to select L2, so we'll do second and number 2 for L2, and that'll bring up the data that I have put in L2. Be sure you press enter so it's accepted that. We'll go to zoom number 9 so we can get a good window to start with. And then we're going to go back and make our adjustments by adjusting the window. So our starting value is actually what we had set up last time. We had set this data to start at 125 because that was our minimum value there. Our maximum, I'm not too concerned about adjusting that. If we go down to our X scale, our class width on this one was 25. Press enter so it accepts it, and then press graph, and we should see a graph. Okay, so we see a graph that represents what we would expect here. If you look back on the distribution, we had 1 value in the first class, 0 in the second 2 classes, and then 3, 34, and 12. So if we're looking at the graph from this calculator here, we can see that we have 1, 0, 0, 3, 34, and 12. The main thing is this is getting cut off at the top. So since we know that the largest class was 34, if we go down and change our Y max to 35 or something close to that, and then look at the graph for it, then we should have a graph that looks like we would expect it to. Press trace, and you can use your arrow keys and go from each class and see what the frequency would be for each one of those. Okay, so that's how to use your calculator to do the histograms. I wanted to take just a minute to hop over to StatCrunch and take a look at that. Okay, over in StatCrunch, if we press open StatCrunch, then I'm going to bring up some data that I had saved. Okay, we've got the McDonald's data. Okay, so here we have the McDonald's data. If I want to do the histogram with that, then I'm going to go to graph, histogram. I'm going to choose this, and for my starting value, I'm going to choose, for that particular example, we were choosing 75 for the starting value, and then we want to, let's go in and edit this a little bit more. We want, for the width, we want to use 50. And again, these were values that we had predetermined on when we were working with this same set of data last class. So I'm not just pulling them out of thin air. They're the starting value and the class width that we had used when we were working with the McDonald's example last class. Okay, so here's the data, that the histogram that you should get when you put that data in and manipulate it with that particular starting value and class width. Okay, so you can see these that have been generated by StatCrunch. They're very nice graphs, just as the graphs on your calculator are. So you have two resources as far as being able to generate your histograms. Okay, moving along, you can have a relative frequency histogram. A relative frequency histogram just simply means that instead of having the vertical axis labeled with your frequencies, then it could be labeled with your relative frequencies instead. So that would be the only difference with that. Okay, when starting to interpret histograms, there's several things that's important to remember. You want to think about the center of the data. You want to talk about how the data is varied or spread out. What is the shape of it, and whether there are any outliers, and also the time factor with that. Okay, so some common shapes that you should be familiar with the distributions. This would be what we would call a bell-shaped or normal distribution. This is going to be symmetrical. It's going to start out low, come to a peak, and then come off on the other side. And like I said, it needs to be symmetrical. Uniform distributions are pretty flat, like a rectangle. So uniform just means that all of these values along the bottom are equally likely to occur. Right skewed means, if you have, look at this graph, it has a larger, longer tail to the right, and left skewed is going to have a longer tail to the left. Okay, so the normal distribution is the one that we like to work with. I will say that we don't live in a perfect world, so our distributions are not going to come out perfectly normally distributed. You have to look at it in kind of a rough sense. And this one, it does increase to a point and then come back down, and so it would be roughly bell-shaped, and roughly a normal distribution. Skewedness, it's when it's not symmetrical and extends more to one side than the other. And so this, like we said, is an example of being positively skewed or right skewed. Those are terms that are used interchangeably. And you have a longer right tail. And skewed to the left, which is also called a negative skew, you're going to have a longer left tail. Okay, the normal quantile plot is also a way for assessing normality. So we're not going to worry about constructing the normal quantile plots at this point, just interpreting them. So a normal, when you're talking about a normal distribution, the pattern of the points in a normal quantile plot is going to be reasonably close to a straight line, and the points do not show some kind of systematic pattern that's not a straight line. So in other words, if you have a pattern that has some kind of curvature to it like this, even though that looks like it lines up pretty close to a straight line, if it has curvature to it like this, then that is not going to be normally distributed when you're looking at the normal quantile plot. So I want to be clear that a normal quantile plot is specifically used to determine if a distribution is normally distributed or not. It is not a scatter plot. They're two different types of graphs. So the normal quantile plot, you want it to line up in a straight line, but you don't want it to have any kind of curvature to it. Okay, so it's not a normal distribution if it either does not lie reasonably close to a straight line pattern, or the point shows some kind of systematic pattern that's not a straight line pattern. Okay, so this is an example here. They're not perfectly in line, but they are fairly close to a straight line. So if I was looking at this normal quantile plot, I would say that there's no kind of systematic pattern. So they're reasonably close to a straight line, so we would say that it is a normal distribution. If I look at one like this, obviously this is not staying close to a straight line, so it would not be a normal distribution. And this one looks very close to a straight line, but if you notice, there is a rounding of it, a curvature that kind of goes up and then it goes down. So anytime that I have that happening, even though it's really close to that straight line, it is not going to be a normal distribution. So here are some pairs. I usually say look at the two in tandem. Look at the histogram and look at the normal quantile plot for both. And we'll look at constructing the normal quantile plot over in chapter 6. But for now, just being able to interpret what's given to you would be the expectation that I have. So this one, it looks roughly normally distributed looking at this. When I look at the normal quantile plot, it does hug very close to that straight line, and therefore we would say by looking at the two of these that this would be roughly normally distributed. If I look down here at this one has a longer tail to the right, so it would be right skewed. And if we look at this, there's definitely some curvature there, and it's coming off of that straight line. So the two of these together would say that that would not be normally distributed. So this is the McDonald's example that we've worked with a lot. If we look at our histogram here, this one would have a tail to the right, so we would have it, say it was slightly skewed, and you can see that this does have some curvature and come off of that straight line a little bit. This one is more skewed, definitely more skewed to the left, and you can see that it's way off of the straight line, so it would not be normally distributed. Okay, moving on to section 3. In section 3 in chapter 2, we're just going to be talking about briefly some different types of graphs and some of the merits that they have and some ways that graphs can be deceptive. Okay, a dot plot is a graph of quantitative data in which each data value is plotted as a point or a dot above a horizontal stack of values. One thing about a dot plot, you can actually go back and retrieve your entire data set. So like if I look at this, I can see that there's 1, 2, 3, 4, 5, 6, 7, 8 values that were 70. So I can count the dots and know exactly what that data value is. So that's important. I can look at the shape of this and know what the distribution would be. So it would be roughly a normal distribution. So even though a dot plot's a very simple type graph, it does give us some important information. So like we said, some of the features, it can display the shape of the distribution, and it is usually possible to recreate the original list of data values. Stem plot or stem and leaf plot, you're probably also familiar with. Basically, if I have the number like 42, then the first digit is going to serve as the stem, and the second part is going to be the leaf. So I put the stems over on the left side and the leaves on the right side. So here, if I were to try to go back and get my data values, I would say 4, and the 4 and the 0 would give me 40 and 42, and then I'd have 50, 50, 52, and so forth. So I can clearly see what all my data values would have been. And if I look at it as being turned on its side, I can still see the shape of the distribution as well. Okay, a time series graph is quantitative data that's collected at different points in time. So it's really important that my x-axis, my horizontal axis, is in time. It doesn't have to be years, but it does need to be time. It could be seconds, minutes, months, years, whatever, but it needs to be time. So a lot of times when you're tracking something over time, maybe the crime rate over time, the stock market, the temperature outside, all of these are things that are changing with time, and tracking that can be important. It can tell us trends. We've seen a lot of time series graphs lately with the coronavirus and how it's spread and how many new positive cases there are each day. So all of those are time series graphs as well that you're seeing. Okay, so it does reveal information about trends over time. So bar graphs, we've mentioned bar graphs a little bit already. They look a lot like a histogram, except they use categorical or qualitative data. So the data is not numeric, it's going to be qualitative. It can be numbers, but generally it's numbers when they are not quantitative in nature. Okay, so the bars may or may not be separated by small gaps. So with a histogram, they're not gonna be separated. They're going to touch. The bar graph, they may touch or they may not. That's not necessarily a characteristic of the bar graph. And it does show the relative distribution of the categorical data so that it's easier to compare the different categories. Okay, so if I look at this one, I can clearly compare the different majors, education, business, and biology for males, and then compare it for females and so forth. So it's just a very clear way to compare those. The Pareto charts is a special type of bar graph. So it has all the characteristics of a bar graph, but it has the additional stipulation that the bars are arranged in descending order. Okay, so because a bar graph uses qualitative or categorical data, we are able to rearrange the bars in a way so that they're in descending order. If it used quantitative, if the data was quantitative, we could not rearrange the bars and it makes sense. So like on this one, this is a Pareto chart because the bars are in descending order. And because we've got jet skis, motorboats, utility fishing, inboard, and sailboat, if we needed to, we could move these bars around and it really wouldn't affect our graph. So that's why this is a bar graph here that we're using. And it's a special type of bar graph being a Pareto chart. The pie chart is a very common graph that depicts categorical data as well. So generally, the larger the slice of the pie, the larger percentage it's representing, and it allows us to see proportions easily. It doesn't give us a lot more information than just the proportions with that. Okay, a frequency polygon, it uses line segments to connect points directly above the class midpoints. So those are important characteristics, and it's similar to a histogram, but it uses line segments instead of bars. So if we look at an example here, and this is again going back to the McDonald's lunch example, here we've got, these were the midpoints for each of our classes. If you go back and look at that example that we did, those would represent the midpoints. And then these would be the frequencies for each of those classes that would be plotted there. With the frequency polygon, you are going to start at 0 and you're going to end back at 0. And therefore you have a closed geometric figure with these straight sides, and that's going to be a polygon. So it forms a polygon. Your graph actually forms a polygon with the horizontal axis there. So it starts and it ends back at 0. Okay, so here's the comparison of the relative frequency polygons for the Dunkin' Donuts and McDonald's. We looked at a comparison in terms of the tables, and this is a comparison in terms of the relative frequency polygons. So you can see that the shape is somewhat similar, except McDonald's is a little bit further to the right than the Dunkin' Donuts. Scatter plot is going to check for correlation. So these you're probably pretty familiar with. You want to see if it has like a linear correlation, if the two data values are correlated in any way, if they affect each other. So it's paired data. You're going to have both an X and a Y. It's also quantitative data, and you'll have the horizontal x-axis and the vertical y-axis. So it's used to determine if a correlation exists between two different data sets. So here would be an example, if you're comparing waist circumference to arm circumference, you've got the plotting of all the points of the data. And in doing that, if it forms roughly a straight line, I've also heard it say if it's kind of cigar shaped in nature, then that is a correlation, then a correlation exists between those two. It would not be a tight correlation, or it would be closer to a straight line if it were a better correlation, or it wouldn't be a strong correlation. Looking at this one, it would not have really any correlation because there's no distinct pattern that occurs with this distribution of points here. Okay, some things to look for when we talk about graphs that deceive, because a lot of times you will see that graphs are used to deceive people instead of actually just conveying information. So a common deceptive practice is using a vertical scale that does not start at 0. So in order for it to be accurate, it needs to start at 0, because when it doesn't start at 0, it exaggerates the difference between the groups, and it deceives in that way. So here's an example of, it's the same information, it's just this one starts at 10% and this one starts at 0%. So by starting at 10%, it's like it just focuses on this part of the graph, and it makes that difference look a lot larger. Because if you look at this, it's not a huge difference between the two, but it does it get exaggerated when our vertical axis starts at the 10%. Pictographs are another way that graphs can deceive. I want to go through kind of a depiction here. If we let this line be 2 units long and this line is 3 units long, so here our difference is only 2. But if we start looking at it as a 2-dimensional figure or even as a 3-dimensional figure, you can see that very quickly it becomes deceptive in how much difference it is. So if we look at the area here of this 2-dimensional figure, that area would be 2 times 2 or 4, and this area would be 3 times 3 or 9. So the difference went from just a difference of 1 here to a difference of 5. And then if we extend this and make it 3-dimensional in nature, so if we have a 3 by 3 cube, this would be 27, and then a 2 by 2 by 2 would be 8. So if I subtract those, their difference would be 19. So when you have something that's like 1-dimensional with a difference of 1, when you turn it into 2-dimensional and 3-dimensional, you exaggerate that difference significantly. So here's some examples of those. Like here, if you're looking at this cigarette versus this cigarette, the difference is like 18% to 38 to 37%. So it's like this is double this one, but this cigarette is obviously way more than double this one because not only did it get doubled in length, but it also got doubled in width, and therefore perceptively to our eyes, it's trying to distort the difference in the data values here. So be careful that you do not put a lot of credibility in pictographs because they can visually distort the data. All right.